So we are going to focus on the functions of random variables, and today we can give a little introduction, a beginning to that topic, and we are hopefully going to spare 3 hours of time in total for the functions of random variables. So why do we have such a name for a chapter? Why functions of random variables are important? First, we need to discuss this and we need to explain why should we study the functions of random variables. Now, you know, the random variable is already a function itself, right? So remember, random variable was what? It was converting the outcomes in a sample space to quantitative values, right? But in real life, we do not just study the random variables, also the results of these randomnesses, okay? So I'm going to explain this, discuss this in the beginning of this chapter. And there is a common misperception about the functions of random variables, about the expected value and the variance, which I am going to show you. And please do not apply these wrong formulations, these misperceptions that are applied by many students. These are totally wrong. I am going to show you these misperceptions and just to warn you that they are wrong, okay? They cannot be applied. Now, by the way, you can hear me, right? You can hear me, my friends? Okay, that's good. Now, let's move forward. Then we are going to talk about the functions of discrete random variables first and the functions of continuous random variables second. So remember, now I have told you this, starting from chapter 4, in every chapter, we always start with a discrete random variable, and then we are going to move to continuous random variables. Okay, chapter 4, chapter 5, chapter 6, and chapter 7. In all of them, we are going to first focus on the discrete random variables, then continuous random variables. And in each part, we are going to see how the expected value and the variance of a function of a random variable is calculated for discrete ones and then continuous ones. And also, how can we determine the distribution of a function of a random variable? Okay, now you see, if we have a random variable, and if you define a function of that random variable, most probably that output of that function will also be random. Most probably, okay? So, for example, when you apply a linear function, linear transformation to a random variable, you remember from the normal distribution, if you apply a linear transformation to a normal random variable, you again get a normal random variable, right? So again, you get a random variable. So usually the functions of random variables are also random variables as well. So our objective today is to understand how can we study the distribution of a function of a random variable. Okay, so why functions of random variables are important? We need to explain that. So what is a random variable? A random variable is a real valued representation of an outcome in the sample space as we know it. For example, imagine an experiment. We are manufacturing products, okay? We are manufacturing products in a batch, let's just say 100 products, a batch of size 100. Of course, because of the problems in the manufacturing processes or maybe caused by other reasons, okay? Some of the products can be defective, right? So almost in all manufacturing processes, we have several reasons for manufacturing defective products. Maybe caused by a human, caused by an employee, maybe caused by the process itself, maybe caused by environmental conditions, right? So in a production batch of 100 products, we may have some defective products. And the number of defective products in a batch is a discrete random variable, right? And usually can be modeled by a binomial random variable. So X can be a good candidate for a binomial random variable. And another random variable, let us define the daily demand to gasoline. The daily demand to gasoline in a gas station, it is a continuous random variable, right? So how much gasoline that you are going to sell if you have a gas station on any day, which is going to be called the daily demand, it's a random variable because it is impossible for you to predict that in the beginning of the day. You can only learn about it in the end of the day when you check the amount of gasoline that is left. Okay, so the daily demand to gasoline, by the way, gasoline is a liquid product, if you see. Therefore, the daily demand to gasoline should be a continuous random variable because, you know, people are not purchasing gasoline in discrete quantities, but they are purchasing gasoline in continuous amounts, right? Continuous amounts. So the daily demand to gasoline is a continuous random variable. So, and it can be modeled by, for example, a normal random variable. So a normal distribution can be a good candidate for modeling the daily demand to gasoline in a gas station. Now, but why I have given these examples? So let's read the next sentence. We are often interested in measuring the benefit or loss caused by a random occurrence, right? So nobody is actually interested in the number of defective products in a production batch. Instead, we are interested in the cost of quality errors, cost of these quality errors, right? I mean, as a manufacturer or as an owner of a manufacturing facility, I am not interested in the percentage of the defective products that I manufacture. I am interested in the costs that defectiveness causes to me, okay? Which is basically a function of the number of defective products, right? So depending on the number of defective products, a certain quality error will occur, okay? So for example, quality prevention costs, or the compensation costs. I mean, if you sell these defective products to customers, right, then you are going to pay some compensation costs, tazminat, right? So all of these costs are called quality costs. And I am much more interested in the costs that are caused by manufacturing defective products rather than the number of them. Or, for example, am I interested in how much gasoline that I am going to sell, or how much money that I am going to obtain from selling this gasoline? Obviously, I am going to be much more interested in the money that I am going to observe, right? So in both of these examples, I am giving monetary examples actually. So if capital X is the number of defective products in a batch, we can define a function which calculates the cost of these defective products, and that is going to be the amount of monetary loss caused by the defective products. And I can define another function, H. So it is going to calculate the daily profit that I'm going to obtain by the daily demand of the gasoline, okay? So how much profit it will bring to me by selling it, by selling this demand. So instead of being interested on the number of defective products or the daily demand to gasoline, I would be much more interested in a function of them, a performance function of them. So we have random inputs here. X and Y are random inputs of my system. So the number of defective products that I produce is a random input of my manufacturing system. However, I am much more interested in the random output, which is the cost of that defectiveness. Or the random input of a gas station system is the daily demand to gasoline, but I am much more interested in the random output of that system, which is the daily profit that it brings to me, okay? So X here or Y here, they represent the random input of a system, while a function of them represent the output or the performance of the same systems, okay? So because of that reason, functions of random variables are important, because usually in real life systems, the inputs are random, therefore the outputs are random as well. So can you predict how much money that you are going to make in your gas station? No. Why? Because actually you can predict it, but I mean, can you predict it? 100% sure. Okay. Can you exactly predict it? Okay. You cannot exactly predict the profit that you are going to make in the end of the day, because you cannot exactly predict the gasoline that you are going to be selling on that day. The input is random, therefore the output is random. The input is random, therefore the function of that random variable is also random. Okay? And we are going to be much more interested in the functions of random variables. Okay? So, given a random variable x and a real valued function, so g is a real valued function, which means from real numbers to real numbers. It's a conversion or transformation of the random variable x. Gx is also a random variable in most of the cases. Okay? If the daily demand to gasoline is random, then the daily profit is also random based on the randomness of the demand. Okay? Therefore, g of x, the transformation of a random variable, will also be a random variable. Therefore, it will also have its own expected value. It will also have its own variance, and it will also have its own distribution functions, such as the CDF, probability mass function, and PDF. So there is a misprint here. I need to correct that one. So the question is this: how can I determine the expected value of a function of a random variable? How can I determine the variance of a function of a random variable? And how can I get to find the distribution of that function of a random variable?